My name is Yang Liu from Jinan Institute of Quantum Technology. I will discuss about the TF-QKD experiments. So since this is a tutorial talk, it will be very simple and basic and only on the experiments. Okay, the talk will be in the few sections, and in the first will be a short introduction, and then will be the essential requirements for the TF-QKD. And then with some of the experiments, I will introduce how we solve the problems and how to build up such a system. And finally, I will talk about a few related works to TF-QKD experiment. Okay, first, since the proposal and development of the quantum key distribution protocol for the past 40 years, the system is already a mature system, and it's possible to build a trunk line like from Beijing to Shanghai for 1,000 kilometers with trusted nodes. You can refer to the last session for detail about the bigger network. And it's possible to build an in-city network with different topologies. For remote nodes, it's possible to connect the system with a satellite. It seems it's already the quantum key distribution systems, and it's only the work to expand the system with more nodes and to connect with different cities and maybe different countries. But we always want something more. With BB84, decoy state, BB84 state, for example, the transmission distance for the commercialized system is generally 100 kilometers. So there will be some of the trusted relays in the rural area and maybe in highway where the security is not good enough. And the practical attacks to the quantum system always targeting on the vulnerable part of the system, in which the single photon detector is one of the vulnerability. So a lot of the attacks are targeting on the single photon detector. So what we want is we want some system that is more secure. For example, the MDX security, measurement device independent security. And we want the system to run with a longer transmission distance. For the previous system, the decoy state BB84 system transmission distance is about 400 kilometers and 21 kilometers with 72 dB of the transmission loss. And the MDI-QKD also transmits to 442 kilometers with about the same transmission efficiency. Even if we can make the system working in longer distance, the secure key rate at this distance already less than 1 bit per second. So for a longer distance, the secure key rate will be even smaller. Okay, the theorists tell us that there is a limit to the repeatless quantum key distribution systems. This we call the PROB bound, naming after the scientist. So let's write down the equation for the repeatless quantum key distribution systems. We find that for most of the systems, the secure key rate is proportional to the transmission efficiency. I'm not talking into detail of the equations, but TF-QKD actually solves this problem, and TF-QKD is possible to increase the secure key rate from the proportional to square root of the transmission efficiency. So that means this protocol is possible. It resembles of a single quantum repeater like secure key rate. And that means it's possible to achieve a longer distance. And for a long distance, the secure key rate is possible to be higher than the best of the previous protocols. Okay, so that is for the secure key rate of twin-field quantum key distribution. So it is a benefit from the protocol. The question is there any problem, and how do we build such a system? Okay. As next, I will introduce the protocol very briefly following the theoretical protocols. I'm using the SNS TF-QKD as an example. The other variant of the TF-QKD protocols will share the similar experimental structure. And this in sensing or non-sending TF-QKD, the theory requires us to take a random phase shift to a coherent process. And this protocol uses a decoy state method. That is, we use a decoy state and signal and vacuum windows to modulate the signals. So in experiment, we do the Z basis and the X basis. In the Z basis, we can encode 0 and 1 with the sending or non-sending process. And we do the random phase randomization with phase modulators. In X basis, we need to encode with different phases. And finally, we need to use a decoy state method to eliminate the potential attacks. So the system, the process will be like in the diagram here. There are different intensities of the signal process with different phases. So that is a bit complex, but still similar to the decoy state BBD4 or other protocols. And in the receiver, Charlie is required to measure out the twin field with a beam splitter for the single photon interference. And they then announce the decoy windows and do the post-processing things. So the post-processing is much more like a theoretical thing. We need to focus on the experiment part. In the experiment, we just need one simple beam splitter to combine the twin fields. To get a Z window, in the Z window, we keep all the single detections. And in the X window, we only keep the event satisfy this equation that when the phase difference between Alice and Bob are 0 or pi, that means a destructive or instructive interference. So until now, the system is not very complex. It is only have this laser to emit the signals and to do the encoding. Like in BBD4, we can use an intensity modulator and phase modulators for the encoding. And we don't only need a detection of the single photon interference with the very simple beam splitter. Everything looks fine, only with one different from the previous protocols. That is, in TF-QKD, we need a single photon interference with independent lasers. So as a comparison, in MDI-QKD, we need a two photon interference. And the two photon interference do not need a phase interference. It only requires a time coincidence. So it only requires the wavelengths from the sources are the same. But here in TF-QKD, we need something more. We need the phase is stable. So how to make the phase stable? We need the wavelengths from Alice and Bob to be exactly the same. And we need the fiber the vibrations from fiber, the phase from the fiber length difference to be controlled or compensated. And also there might be some initial phase in the system we need to calculate or compensate this initial phase. So here we generally need a locking or compensate mechanism to make sure the laser wavelengths from Alice and Bob are first narrow line-wise and second to be exactly the same. And we need to compensate or calculate the phase drift from the fiber channel. That is the essential thing for TF-QKD system. Okay, so next I will talk about the method we need to perform these mechanisms. So now we need the system with a few things more. Generally we need a seed laser to send in the seed wavelengths to Alice and Bob, and we need a frequency locking mechanism to lock the local laser to the remote seed. So now we have the same wavelengths from Alice and Bob. Then generally we need a phase reference to do the phase compensation at Charlie. In the practical system, we may need a feedback system for the whole system to be running. So that is all we need for the TF-QKD system. For the laser, there are different kinds of lasers. For example, the general laser we use for the decoy state BBD4 protocol, we generally use a DFB laser. The line-wise is about tens of megahertz. And we have narrow line-wise the cavity laser, we have the ultra-stable laser. We need the laser to be very narrow line-wise for the long coherence and for the interference. So next, I will talk about the phase drift and the sources of phase difference from the the fiber channel and from the source. For the channel, we send a narrow laser to the interferometer, and for example, when it is a balanced Mach-Zehnder interferometer, the interference will be stable. Stable means that the phase kept almost stable during the second of the time scale, and we can calculate this amplitude to the phase drift. And from the phase drift, we can calculate a phase drift rate. For this single laser, it is almost stable with drift rate less than 1 radius per millisecond. But for a fiber channel with 100 kilometers of fibers, it will oscillate very fast. In the 5 millisecond time scale, you can see the drift will be a few to per range. So with this amplitude, interference amplitude, we can calculate the drift rate to be about 1/10 of the radius per millisecond. What about in the field fiber? It is a bit better actually. The drift rate is about 3 radius per millisecond. This comes from that the in-field fiber is always a buried fiber. It can be buried in the ground, so the vibration and the sound noise will not affect the phase of the fiber. But in the lab, there might be sound, and maybe there are fluctuation of the temperature from the air conditions. So that will contribute to the drift rate of the fiber itself. Okay, after talking about the drift from the fiber, there are the drift from the laser itself. Even if we make the two lasers, the wavelengths of the two lasers are about the same, we can see that the drift rate is still high. Okay, the time scale is 0.2 millisecond. And this oscillation comes from the frequency difference of the two lasers. It can be called the Huntington interference. So, and even if we make the wavelengths of the two lasers to be the same at one time, it will drift away very fast. So we need some mechanism to log the wavelengths of the two lasers together. For example, we can log these two lasers to the ultra-stable light state, and after logging, the interference is stable. This picture is taken from the April 2nd time scales, so it will be stable in April 2nd. And the drift rate after passing 500 kilometers of the fibers will be about 10 radius per millisecond, which is almost the same to the result without the two lasers, with one laser. So that means it's possible to just lock the laser and use that as a source for interference. And we can do some statistics after this the interference result on oscilloscope. We can take the time into slices and we statistic the standard deviation of the phase drift in each slide. After that, we can do a histogram to see that the phase drift for each different timing period. Okay, so we can get a statistical result for this phase fluctuation, for example, in 100 kilometers. In this picture, we can find that, for example, when the standard deviation of the phase drift is about 8 degrees, the time range is about 90 milliseconds. That means we can take a period of about 90 milliseconds for statistics for the phase of the different fiber, Alice and Charlie and Bob to Charlie. So with 8 degree of the standard deviation, that means the QBER is about, the baseline QBER is about 1%. We do not want the baseline QBER from this phase compensation to be too high to be a harm to the system of the phase error rate. So we can take different scenarios we can do the 100 kilometers in field, and for example, the 300 kilometer fiber, we can safely take the time range for the phase estimation or the phase correction to be about 20 or to 30 milliseconds. This is a time scale that guarantees the baseline error to be about 1%. We can take another perspective from the frequency perspective. In the frequency, it is also a statistical perspective. From this variance of the phase fluctuation, it's possible to just calculate the QCrypt with this equation, and with Wiener-Kirchhoff theorem, it is possible to calculate the variance of the phase fluctuation from the phase noise PSD. And PSD is possible to be measured directly from spectrometer. So it's possible to see that one thing is possible to see that with a stabilized and unstabilized laser, the frequency difference in the PSD is different. The time range for the phase estimation is different. We can also estimate the noise source from the laser and from the fiber from this perspective of frequency perspective. With this perspective, it is also possible to calculate the allowed path difference between Alice Charlie and Bob Charlie and the other parameters. Okay, now we have the system with seed laser and the frequency lossing system, and we need a system for the high-speed uniform encoding and for the phase reference compensation mechanisms. Next, I will use a few of the experiments as an example to show how we can build the system. One of the simplest architecture is using the SegNAC architecture. In the right, we also see the equation for our requirement for the phase stabilization. For the SegNAC loop-based experiment, we just need to use one laser. The laser is sending either clockwise or anti-clockwise. So the wavelength of the laser is kept the same because we just use one laser. The phase from the fiber will be compensated passively because of the SegNAC architecture. In the experiment, this experiment shows that the visibility is possible to be 97% in 200 kilometers of the fiber distance. We note that in this SegNAC architecture, the backscattering noise will limit the long-distance signal to ratio because the backscattering noise will be combined with the signal from the other direction. Another possible solution is for the wavelength difference is to use a laser injection. The laser injection is done by using a seed laser sending from Charlie to Alice and Bob. And Alice and Bob, it will be sending to the laser diode, either in the reflection or in transmission mechanism. And with this laser sending, the slave laser will follow the wavelength and the phase of the master laser. In the left or the right diagram here, will show that the interference shows it is possible to achieve a good interference visibility, and it is good enough for the TF-QKD experiment. But we actually, in the previous experiments, there is a light sending directly into the encoding system of the TF-QKD. We always hoping that the external light is not sending directly into the encoding. So we can use ultra-stable laser and time frequency dissemination mechanisms. The ultra-stable laser will solve the problem of the wavelength difference. An ultra-stable laser is generally a narrow linewise laser locking to the ultra-stable cavity. And with this, this is also always done with a PDH locking mechanism. The ultra-stable laser may have a linewise of less than 1 Hz, and the frequency drift of the ultra-stable laser to be less than 1 Hz. That means it is already possible to perform the experiment without any locking. We just need to calibrate the laser before experiment. And then we can leave the system running for an hour and then locking the system again. Because the drift rate is not very much. But we can perform a time frequency dissemination mechanism. This is done to sending the light from Alice through the fiber lens to Bob, and then the Bob, the frequency shifted light of Bob's astral stabilizer is beat with the Alice laser to be a hand-to-down detection, and it is possible to use an AOM to lock in the frequency to a fixed value. The light from Bob is also sending back to Alice for the stabilization of the phase drift and the frequency drift in the channel. With this mechanism, it is possible to lock the frequency of Alice and Bob's laser in real time. After the calibration of the fiber wavelengths, it requires to calibrate the phase from the fiber. We can do this by using a stronger phase reference light time deviation with quantum signal. With this mechanism, we can send for different phases. For example, the 0, pi O2, pi and 3 pi O2. We know that when interference at Charlie, when the two of the pulses are interference and destructive interference, the other two will be almost in the middle, and that will be the sensitive part. So we can build a simple error model, and by minimizing the additional parameter, that is the phase difference in the channel, we can achieve this value from the fiber channel. Besides this post-processing based method, it is also possible to perform the phase tracking in real time. In real time, it is possible to lock in pi over 2 phase difference, which is in the middle of the interference. That is the most efficient solution to the interference. For example, here, when the feedback is off, the blue line shows a very fast oscillation from the fiber. And when the feedback is on, it is almost at 2 over pi. And in the rightmost figure, when the feedback is off, the interference result will distribute uniformly at different phase differences. And when the feedback is on, it can be centered at pi O2. Okay, with this frequency and phase locking mechanisms, you can already build a very simple TF-QKD system with this frequency stabilizer and frequency locking mechanism, and with this encoding part, and with fiber phase difference compensation and post-processing. With this very simple experiment, you can achieve more than 300 kilometers of transmission distance, and without much of optimization, the security rate is already higher than the PRV bond, the repeatedly the QPD security rate. And here, when observing the error rate from the phase x basis, you can see that the QBER in x basis is not very much. It's actually small. That means the phase and the frequency locking mechanism working is good for TF-QKD systems. There is a theoretical improvement to improve the performance of TF-QKD in post-processing. I will introduce it very briefly. This is a two-way communication because the error rate in X and Z basis are quite different, and the error from Z basis are generally from the coincident detection from the sending and sending events. It is possible to eliminate this error by two-way communication. In two-way communication, we mean that we pair the pulses from Alice or Bob to be, we pair two of them to be a pair. And we can do the parity checking. We drop everything that the parity is not the same. So we keep the pulses pairs with the same parity. that will decrease the QB in Z basis and will increase the QB in X basis. But generally, it will be a benefit for TF-QKD system. In theory, they observe that the parity distributed not evenly. For the even parity pairs there, the QB rate is higher, and for the odd parity pairs, the QB will be smaller. So it is possible to keep only the odd parity pairs, and what's more, it's possible to actively grouping the odd parity pairs to minimize the QB in X basis, in the Z basis. So, for example, okay, this figure is ruined. So anyway, you can see these numbers. The blue line is a PLV bound, and with a two-way communication, the security rate in this experiment is already higher than PLV bound. With odd parity pairing and with the AOPP pairing method, it's possible to increase the security rate by a few times. So that increase coming from one is from the decrease of the QB, and the other, it is possible to increase the time ratio of the sending pulses for TF-QKD. With this improvement, it's possible already to achieve 500 or 600 kilometers of the transmission distance. Here, the security rate of TF-QKD already shows the advantage. It is a few orders higher than the decreased BB84 and MDI-QKD at this 400 kilometer fiber distance. And when the other protocols cannot achieve a security rate, TF-QKD is possible to achieve a security rate, and it is already higher than the absolute PLV bound, where we set the transmission efficiency and detector to be the ideal in Charlie. TF-QKD is a phase-sensitive system, which we always struggle with phase variation in the fiber. But that means TF-QKD is a good sensor to the phase variance of the fiber. So the phase variation coming from the vibration of the fiber, so we can actually modulate some vibrations. We can recover this frequency from hertz to kilohertz. And with the two-point positioning method, it is possible to positioning the time difference and to positioning the point of the vibration with accuracy better than 1 kilometer. And the right is showing that when the frequency, 100 frequency is showing to set on and off with a TF-QKD system, it's possible to recover the phase difference around the time with this time frequency analysis and the diagram. Okay, in previous we used the ultra-stable cavity. It's also possible to use other mechanisms. One of the most common mechanisms to lock the laser frequency is using the optical phase-locked loop. This phase-locked loop is generally like you sending a seed laser from Charlie to Alice or Bob, and sending a local laser from Alice or Bob to interfere with this external seed as a hand-to-hand detection, and with this beating rate result, we can fix the beating frequency to be a fixed value with PID algorithm. And this is done with fast tracking with the AOM inside the OPL and the slow tracking mechanism in the PCT and the laser. With generally a common seed laser will be about 1 kilohertz of the line width. It is also possible to use a homodynamic detection instead of the hand-to-hand detection shown in the previous slide. With the homodynamic OPL method, it will be possible to avoid the noise of the electronic phase detector and the local oscillator in homodynamic. So it can be showing a better interference result using the hand-to-hand OPLL. That means that the narrow histogram for the phase drift. So with with this result, we can think about how to push the system to longer distance. For a transmission distance longer than 600 kilometers, we need to consider the system noise. One of the noise is from the strong phase reference light. Remember that we generally send a stronger phase reference light than the quantum signal because the intensity of the quantum signal is fixed as the output of Alice and Bob. But for a stable phase compensation, we need the phase reference to be strong enough that we achieve about 1 megahertz of the counting rate at Charlie. So that means the phase reference will be a problem for long distance TF-QKD systems. The noise may come from the Rayleigh scattering. The forward Rayleigh scattering is coincident with the quantum signal. It does not matter, but the backward Rayleigh scattering will be in different directions, but the backward of the backward Rayleigh scattering will be in the same direction, and it will be uniformly distributed in time scale. So that can be a problem, and we call this Rayleigh scattering. This Rayleigh scattering shares the same wavelength with the quantum signal, so cannot be filtered out very simply. And there can be other mechanisms. The Brillouin scattering is a small wavelength different from the reference signal. And Raman scattering is generally a broadband. And this kind of noise can be filtered with wavelength division. There can be reflections from SNSPD, which we need to be isolated. Okay, so we can model the Rayleigh scattering Rayleigh back scattering noise. The total power can be described in this equation, and with a simple integration, we can achieve the Rayleigh scattering power to be in this equation. So, for example, we set the intensity of the reference light to be about 2 megahertz at Charlie, and the scattering noise is about 10 megahertz at 650 kilometers. This can be a problem for this kind of long transmission distance TF-QKD system because the quantum signal is already very weak. One solution was proposed that is a dual band stabilization. In this method, the wavelength of the phase reference light is different from the quantum signal. So we can actually stabilize the phase reference light first, and then stabilize the quantum signal with a much weaker reference. So the phase reference light can be filtered with a wavelength division modular, and this will eliminate the noise from the phase reference light. So that means it prevents the Rayleigh scattering and the signal wavelength. With this method, and this experiment showed it's possible to achieve more than 600 kilometers of the transmission distance. Next, you already have the tools to push the system to be longer distance. And to perform the experiment is not hard. You only need to increase the transmission efficiency of the fiber and the optical element and the detector, and to decrease the system noise from the fiber and from the detector. In the general fiber, the attenuation for single mode fiber is about 0.2 dB per kilometer. With commercialized ultra low loss fiber, it's possible to achieve 0.16 dB. And using a pure silicon technology to reduce the doped germanium in the core and to decrease the fixed temperature in fabrication, it's possible to further limit the attenuation to about 0.15 dB per kilometer. And in practice, it's possible to measure the 0.157 dB per kilometer for 1,000 kilometer fiber distance. With this fiber, it's also possible to use a larger effective area to reduce the nonlinear effect in transmission. in reported, the transmission attenuation can be about 0.14 dB per kilometer. Also, it's possible to use the post-processing method, post-processing phase compensation method to eliminate the use of the active phase modulator actually, which is a few dB of the attenuation. And you need to increase the detection efficiency. And for the system noise, one of the most important noise from the single photon detectors. The superconducting nanowire single photon detector is one of the best detector. The dark count noise from this kind of detector generally is from the black body photons. So the essential thing is to filter out all the black body photons. For the longer wavelength photons, it's possible to filter the longer wavelength photon with a covalent fiber at 40 Kelvin stage. And for the shorter wavelengths, shorter than 2 micron wavelengths, it's possible to insert a bandpass filter at 2 Kelvin stage to filter out the black body photons. And generally, a DBR-based optical cavity is used to enhance the system efficiency. So with this 85 transmission efficiency of the bandpass filter, it's still possible to achieve about 60% of the system efficiency, with the dark count rate decreased to be 0.02 Hertz, which is ultra low. At this ultra low single photon detection noise, the radio scattering is eliminated with the dual band stabilization, but the Raman scattering can be a problem. So you can use a time multiplexed dual band stabilization method. You'll see that when the strong phase reference light is on, the system noise is about 1 count per second, and when it is off, the system noise is 0.02 count per second, which is almost the same as the single photon detector background. So the next thing is to use a post-processing method for phase compensation. This can be done with a strong phase reference light to calculate the phase first with the same method talked before, and then we just unfold the phase reference, and this already decreased the phase drift by 1,000 times. But we can do it better by considering the phase difference of the phase reference light and the signal light. When considering this lambda 2 over lambda 1, it's possible to achieve almost a stable phase in the signal wavelength. Then we need to estimate the initial difference between these two wavelengths. So this can be done using still using a MIR model, but with 360 more state with this strong phase reference difference. Still, it is possible to just minimize this MIR model to achieve this initial phase difference. There are also other systems to help the full system running. For example, we can use the arriving time of the strong phase reference light to calibrate the arriving time of the quantum signals from Alice and Bob to Charlie. It's possible to keep the relative delay to less than 10 picosecond. The intensity feedback system is also recommended in Alice and Bob to keep the fluctuation of the signal to be less than 1%. The polarization feedback is also used in the system to keep the both of the wavelengths to be stable, stable for the interference. So now you have the system like this with 1 GHz frequency and have every component encrypted. With this system, it's possible to achieve more than 1,000 kilometer, 1,002 kilometer the transmission distance, both in the asymptotic limit and considering the fitness size effect. When we do the shorter distance experiment, it's possible to use a larger time scale for the quantum signal and the smaller time scale for the phase reference light. And it's possible to use a higher efficiency single photon detector, although with a higher noise. So it's possible to achieve more than 100 kilohertz of this QK rate at 200 kilometers. In the previous experiment, the seed laser is used for the wavelength reference for Edison bulb. It's also possible to use absolute reference for TF-QKD. Before, in the MDI QKD, the HCN gas-based absorption method is used, but the source is not good enough for TF-QKD because the frequency difference is about 1 megahertz. This frequency difference is mainly coming from the Doppler widening of the spectrum. With a saturated absorption method, it's possible to eliminate this widening. So it's possible to achieve about 100 hertz of the frequency difference. This is the interference result from two absolute reference light. The phase distribution is about 16 radians per millisecond. It is about the same order as the 100 kilometer of the fiber spools. So that means it is not a problem for QKD. It's already possible to be stabilized with phase estimation or phase compensation method we talked before. With this source, this experiment showed the possibility to achieve more than 500 kilometers of the transmission distance. With the Kuiper in X base is about 4 to 5%. That means the system works fine with this kind of source. Another source without using the seed is using the FFT-based tracking method. When using the strong light to interference, the interference pattern will be oscillated. We can count for the frequency of the interference. But when using the single photon interference, the detection will follow will collapse with the probability using this equation. So it is possible to assign the result to the sequence and perform a FFT based on this sequence of the detections. With the largest amplitude selected, it's possible to achieve the initial phase of this spectrum. And this experiment recommended using the padding zero method to increase the spatial resolution. With this system, the experiment shows that the Kuiper is about 4 to 5%, and the transmission distance is also higher than 500 kilometers. That means it's possible to use this source as a source without the seed light. When using this external kind of laser, the frequency drift can be up to 30 megahertz over 1 day, but this method solves this problem by setting this frequency mismatch to be 100 megahertz. So the frequency drift will not be a problem. The count rate of this method should be a bit higher to be about 10 to 20 megahertz for the reference frame per second. The previous experiment was done in the lab. But it's possible to perform TF-QKD in the field. What's the difference? One of the difference is that there can be crosstalks from the different fibers. So generally, DWDM filtering should be used to eliminate any noise from the other fibers from classical communications. And one other thing is the timing drift of the infield fiber is faster. The blue line and the red shows the timing drift without compensation. It follows the temperature drift. So the delay drift should be compensated with a synchronizing method. The polarization and phase drifting should also be corrected. With all the feedback systems, it's possible to achieve more than 500 kilometers of the field test from, for example, from Jinan to Qingdao province of the cities. And it's also possible to use a optical frequency comb to calibrate the frequency of the different from the for the quantum and the reference light, and it's also possible to push this limit of the in-field test to 560 kilometers in field and more than 600 kilometers when in the asymptotic period. You can refer to the talk in tomorrow morning for this experiment. The experiment talked before was outperformed with a single superconducting nanowire single photon detector with the best performance. But when commercializing and when considering the practicability, it's recommended to use indium gallium arsenide APDs as a single photon detectors. With this kind of the single photon detector, the efficiency is lower and the dark counts is higher. But what's more important is that there is other pulse that means of a few percent. So the after pulse can be a problem if we're using the same wavelength of the phase reference light. The strong phase reference light will induce a strong background noise due to the after pulse mechanisms. So in this experiment, uses the off-band stabilization method to separate the detectors for phase reference and quantum signal. That's to eliminate the after cross contamination from the phase reference light to the quantum signal. So this experiment achieves 254 kilometers at 56 dB between the cities of Frankfurt and Kiel in Germany. The experiment talked before was outperformed in the fiber channel. When considering this free space channel, there are a few more problems to be solved. One of the problem is from the atmosphere turbulence. So no one knows before if the atmosphere turbulence is too fast for TF-QKD. This experiment shows that the phase variation due to the turbulence is almost the same as 100 kilometers of the fiber channel. So it is possible to use a similar technology to compensate the phase drift of the free space TF-QKD systems. As another problem is from the laser sources. There is no additional channel for the free space TF-QKD system to lock the frequency of the two lasers. So this experiment uses a single photon interference to calibrate the frequency difference between the ultrasound lasers and then cancel this frequency difference using AOM. With this experiment, it shows it's possible that another thing is about the channel efficiency. The point where the channel efficiency between Alice and Charlie and Bob and Charlie to be almost the same as selected to optimize the performance of the system. Okay, in the next few slides, I will talk about a few other experimental considerations related to TF-QKDs. One consideration is the patterning effect. Patterning effect was proposed in 2018. It shows that it first discussed in the decoy state system when the intensity of the current pulse might be affected by the previous pulse. For example, when the previous pulse is used as the decoy or vacuum, the intensity is slower than the pulses when the previous pulse was a signal pulse. So this can be this problem can be from the bandwidth limit of the signal generator, amplifier, cables, and modulators. And this it is not only the mean value of the intensity deviated, but the waveform can also be distorted. This might also be a problem if we do not consider this thing in TF-QKD. For example, when considering the intensity, when the previous pulse was a vacuum or decoy, the intensity is higher than when the previous pulse was a signal pulse. But it's possible to compensate with a different method. One method is using a pre-compensation method to set a different voltage for the different pulse pattern. It is possible to achieve less than 1% of the pulse difference for using the pre-compensation method. This can also be a problem for the phase modulation because we have 16 different phases with 16 differences in before. So when we draw the picture, we see that the phase and the pattern of the phase can be different. Also, with pre-compensation, it is possible to compensate all the phases to be almost in ideal state. One other consideration is security. When we do not take care of the component, for example, if the efficiency of the AOM was not well calibrated, it's possible to actively modulate the injected wavelengths of the OPIL mechanism. It's possible to increase the mean photon number in this experiment to about 8%. So that will affect the security of the TF-QKD system. So that also means we need to calibrate and we consider every component before using in the system. So that leads to another protocol we call the set channel secure QKD. In this protocol maps the perfect state of virtual perfect protocol into imperfect state using the real protocol. So the only assumptions left is that if cannot access inside Alice and Bob's labs and the source need independent or other time windows. It solves the other multi-dimensional channels in like TF-QKD systems. You can refer to the poster section for the detail of TF-QKD experiment. One thing we can show that is possible to achieve more than 100 kilometers of transmission distance, and the secure recurrence rate is almost comparable to the original MDI-QKD experiment. The final protocol I would like to refer is the MP-QKD protocol. And this protocol takes advantage of TF-QKD like as it quadratically improved the successful detection event. And it also takes the advantage of MDI-QKD, that is requires a stable optical interference, but not as high as TF-QKD. The structure of the MP-QKD is kind of like the MDI-QKD, but it takes pairs with different positions. So this protocol, generally this protocol will share a easier frequency compensation method because it does not require the global phase and is sharing a good transmission distance and the secure key rate. There are quite a few experiments in the recent years, and you can refer to the talks tomorrow and on Friday for other experiment on MP-QKD. And this is the final of my talk. Thank you.
Thank you very much for this very nice talk. I certainly learned a lot. Are there any questions at this point?
Okay, thank you for your talk. And my question is, in the slides of the improvement of post-processing, you said after Alice and Bob gets their key bits, they manually pair their pulses and compare the bases and the bits. And my question is this processing will be done for the whole string, then will it be secure, or this processing is just for some test bits, then how Alice and Bob knows the remaining key bits will be correlated? And thank you.
Okay, your question is about the implementation of the two-way communication and maybe the LPP method. The first answer is that the two-way communication is performed on the whole string of the raw bits. And the second answer is about the detail of the the two-way communication. Two-way communication was proposed in about 20 years before. It's not something new. The general idea is just to pair the pulses. You have one, you can pair two pulses together and compare the parity of the pulses. You do not need to compare the basis in this step. Actually, this protocol is implemented after the basis selection. We only perform the two-way communication or LPP method after the basis selection, and we perform it on the basis of this protocol. And when using this method, the security is already proved in the earliest article. The most simplest way is to say that the QBER of the Z basis decreases, but you can calculate the QBER in X basis. It's almost double.
Thank you very much.
There's one more question over here in the front.
Thank you very much for the talk. You were showing those influences that would limit increasing the transmission rates, or basically the detection rates. You had a slide where you listed the impacts like scattering in the fiber.
Can you speak a bit slower?
You showed on one slide the fiber effects that limit the transmission rate, and I think I didn't see chromatic dispersion being listed. So is that completely negligible?
I think you mean this slide? Well, I only.
I think it was another slide, but
could you,
so I know that at least for prepare and measure systems, that can be a limiting factor.
Mm-hmm. Okay. Which slide do you mean?
Sorry, I forgot to write down the slide number.
What is about?
Yeah, it was a slide with the different scattering, like Rayleigh scattering, Raman scattering.
Yes, yes. The mechanism for the noise source, I think it should be like, the other direction, Is it this slide?
Yeah. Exactly. So did you also consider chromatic dispersion?
Yes, yes. One should consider chromatic dispersion in TF-QKD system. Generally, I think I just lost this. Thank you for this. You use DCM to compensate the chromatic dispersion in TF-QKD system, but that does not introduce error. It does not introduce noises. It might be introducing errors when the transmission distance is larger than 500 kilometers because the pulse is widening. But generally, it is not a big problem for a TF-QKD system.
Okay, thanks.
There's one more question one over there. Okay.
Thanks for this interesting talk. I have a question about this particular slide. What is the advantage of using injection locking for those lasers? Why cannot you directly use the incoming light that comes from the ultra-stable cavity as the signal?
In this particular slide, the experiment does not use the injection locking. In this experiment uses the optical phase lock loop, and to compare the injection locking and the phase lock loop, for myself, I think injection locking, all the input light is sending to the encoding modular of Alice Bob. There might be some choice house loophole, I don't know. But for the OPLL system, it seems to be better because the light from the local laser is split into two parts. One part is for QKD, the other part is sending to interference with external laser. So the external laser will not directly passing the encoding modelers.
Okay, thank you.
Thank you. Thank you, Jan Glu, for a nice talk. My question is about the compensation mechanism. You mentioned that you can compensate actively with hardware in real time, or you can compensate in post-processing the phase fluctuation. Which method, in your opinion, is better, and in which case? Thank you.
Yeah, thank you for your question. To compare with different phase compensation method, I think it will depends on different protocol and different system requirements. For most of the system, I think both methods will work just fine. I have compared the performance of post-processing and with the real-time compensation method. The performance is similar with the same input signal counter rate. The QBOR are not much different. That can be a bit different. Depends on the specific mechanism of each modular. So different people make different modelers. The performance might be similar, might be different, but that's not a principal problem. But for some of the protocol, for example, in the SCS side channel secure QKD protocol, it requires that we use active compensation method because that will increase the security rate by a few times. So I think that depends. Another thing I think we need to mention is that using the active compensation method, there will be a phase modulator inserted entirely for faster tracking. That will induce about 2 dB of the insertion loss. But in the post-processing method, it requires that we calculate everything in real time very fast. So that will be a problem for the post-processing. So you need to compensate.
Thank you.
Are there any other questions? It doesn't seem the case, so maybe I can ask one question. Like, I guess the questions up until now were more by experts. I'm not an expert in quantum key distribution, so I just have one curiosity. At some point, you mentioned that you could measure the frequency difference by single photon interference. At some point, you mentioned that.
I think it's like in here.
And I was wondering, I guess I can see how you can measure the absolute value of the frequency difference by single photon interference, but I don't know how to measure the sign.
No. First, this experiment is performed by Feihu there, and then for me, I think simply the answer is you can just set the frequency difference to aliases. The frequency alias is larger than Bob, and the second simplest answer is that the sign does not matter. Why? Because only the frequency difference matters, and the sign will affect the initial phase of the FFT result. So actually, it does not matter to the result of the FFT-based tracking method.
Okay. I was just thinking if you want to compensate afterwards, you need to know the sign.
And this experiment does not compensate the frequency drift. It just calculates the frequency and the phase. So it's a post-processing based method.
Thank you.